Alright, BC kiddos. Well, you can't see my face, but you can hear me. I'm at school in a very empty classroom. Pretty late at night, don't think about it. So here's what I'm doing today. I'm going to go ahead and introduce you guys to Edpuzzle. You've probably seen it in like French or some of your other classes, etc. I didn't feel like we really got to finish the vector section on Friday, and I'm seeing a lot of questions pop up. I know homework is due tomorrow. So what I was thinking is, instead of like jumping into polar area, which is probably one of the hardest topics, I don't think it's as hard as Lagrange, but it is tricky. There are definitely other hard things throughout the year, but instead of jumping into that for Tuesday morning for what pops up for you guys, I thought we'd take one more day on vectors. But since your homework is due in the morning, I figured I would give just a couple hints. And sorry, I've been talking a lot this afternoon. My voice is tired. I apologize, man. Okay, I thought since we weren't going to start polar areas until Wednesday, or at least the video won't pop up until Wednesday, having that homework I think be due on Friday or Monday. So we'll have a few days to work on the next section, which is 11.3, that we could take a little more time on 11.2. So in just a bit, post it in your Google Classroom about the same time this video shows up through Google Classroom, but through Edpuzzle. There is a question right here that I've attached that I want you guys to work on. It will be like your homework for this extension of section 11.2. But I'm also going to make the deadline for 11.2 tomorrow midnight, just in case some of you guys want to pop in tomorrow. And maybe watching this video might kind of just spark a few things, like, oh, hey, I don't have as many questions as I thought, etc. I can still look at those homework questions, but I thought I would just do a short, brief one that maybe not everyone will need me to do the homework questions, but I did think, okay, we didn't do very many examples, number 1, endeavor number 32, we barely talked about, and then I'm going to go ahead and pause the video, make sure you guys try your homework, and then I will go over the example that is your homework due Thursday morning by 8 a.m. And you guys can use the video to grade and see how you did and see if maybe your understanding of vectors is a little bit better. We will eventually go over those questions once again. My ideal of what I think this is going to be like, because I'm making everybody watch this video, so just doing a quick introduction, is that I'm going to be posting my videos on Google Classroom through Edpuzzle, basically using my YouTube channel, yes, but going through a platform that's hooked up to Google Classroom, no need for new accounts, etc. You guys will just click on it. And basically, I will be able to see if you watch the videos. So it's kind of just my way of keeping you guys accountable, making sure that you guys are tracking, etc. But as such, I'm not going to make these videos necessarily like all the stuff we normally do every day in class, because not everyone needs that. So instead, if you guys are asking homework questions, etc., I will probably put those in separate tutorials that I attach into the assignments themselves, throwing a quick comment like, hey, here are the explanations of some of the ones that you guys were asking for, and I will try to be available like Monday through Friday, whether it's at school or whether it's at home. I'll try to be live during your actual class period during the day. I mean, I'll probably just be working on work because I have tons of stuff to catch up on as far as grading, because I've been working on technology and revamping some things, etc., instead of working on what I normally do weekends, which is a lot of catching up on grading. So anyway, I'll just be in a Zoom session. I'll probably just post those links online. You guys can pop in. You can ask me questions. You can ask me questions on homework. You can, once we start doing like AP practice and practice tests, etc., you guys can pop in and ask me your individual questions. So that will be a great time just during your normal class grade. Not that you're required to be there. You're required to watch the videos that I post through Edpuzzle, which will be the short, sweet versions of sections. And we're almost done, guys. 11.1, 11.3. And then you'll be required to do things like the test review, the practice test, and then practice AP tests. And I might have you guys do some things like, how do I give a test on Chapter 11 if you guys aren't going to be here, which it's pretty certain that you're not going to be. I might have you guys use your camera and record going through an FRQ or record going through a question. And I just kind of have some random ones that I throw out there, maybe give you some multiple choice. AP Classroom assignments are going to be one of those required things. Just keep an eye on Google Classroom. Just trying to let you guys know that I'm considering. I know some of you don't need as much as others as far as topics and as far as practice. You don't want to force everybody to watch every single video I make. But the ones I do expect you to watch are the ones that are going to be posted as assignments in Google Classroom. And they're for preparation in the homework assignments that should follow. Okay, anyway, this is one of those that's required to watch just because I wasn't going to do a couple extra examples. Number one, and then at the end of this, once again, I am giving you the answer key for the question, the extra question, the extension of 11.2 vectors that comes up. So here's the endeavor card that we talked about on Friday before Victor's creative promposal. And we were talking about position, velocity, acceleration, like vectors have come back. I circled speed, displacement, and the magnitude of acceleration. That's this last guy down here, just because they're weird. You're used to this whole absolute value notation, like you're used to that. Most of you don't remember that the magnitude of vectors was found by basically the hypotenuse, like taking the horizontal change and the vertical change, and in this case for speed, taking the horizontal component of velocity, the vertical component of velocity, and trying to figure out that overall. If we're thinking about like our x prime of t could be this way, our y prime of t could be this way, and then ultimately we are just kind of finding that hypotenuse as far as the magnitude of the speed. But anyway, all that to say, that's where questions are going to get kind of weird, but that's not the only place. Let's go ahead and zoom in on this page that we weren't able to do on Friday. I also want you guys to get down specifically at rest, even though we talked about it. And so at rest specifically, quick reminder, the at rest is when a particle's speed is 0 in both directions, or its velocity, maybe a better way of putting that. A particle's speed, its velocity is 0 in both directions. Because if we're talking about parametric movement, probably velocity is a little better way of saying that. So in this example up above, we have the position of a particle moving in the xy plane. Remember, I said on Friday that is a huge clue phrase or key phrase as far as moving in the xy plane. That is parametric. Given by the parametric equations, okay, they made it obvious. X is equal to, etc. Y is equal to, etc. For what values of t is the particle at rest? So, giving you a quick second to think. Wish I could call on you. Wish you were here. Not this time of night, though. At rest. Well, we know that velocity, in our normal context of motion, velocity is 0, right? But at rest, we just need both directions. That's the key. And so, hopefully in homework, this part didn't confuse you too much as far as at rest. It's more, I just want it in your notes. So x prime of t, we would solve for that guy. Y prime of t, we would solve for that guy as well. Ooh, you guys aren't here to double check my work. T minus 2. I guess you can comment on the video if something goes wrong, huh? And then I have 6 and t squared minus t minus 2. And so I have either t equals, if I'm setting this equal to 0, right, because I need it stopped both, not just stopped vertically, not just stopped horizontally, but stopped at both. I would have t equals 0, or 2 is when it stopped horizontally. But in this one, yes, I have that shared time at t equals 2, but also -1. So I have to think about what's in common. I have to think about what's shared. And the only time that's shared where they both will be 0. So the only time when the particle is truly at rest is at t equals 2. If I remember right, this yellow highlighter doesn't show up too great anywhere else except for the classroom. So let me go ahead and just change it to red. And then if you had to give a justification, you would just say because x prime and y prime both are 0 at that time. Now, as we go down to example number 8, at time t greater than or equal to 0, a particle in the xy plane, see that wording, has a velocity vector given by, oh, there's that component, well, it gives us the components, the horizontal and the vertical components of that velocity vector. So it says, what is the acceleration vector? Once again, it's not a hard concept, it's just things that most of us aren't used to. So if we're trying to find that acceleration vector, just remember with these components, I have to keep it in components. Also, the great thing about acceleration is it's really not all that bad because we just have to keep them in their separate components and take the derivatives like we would normally do from velocity to acceleration. Now, if I want at 3, no big deal. This isn't near as bad as when we were doing equations of tangent lines with parametric, because they give us the time, we can just plug it in. So 2 times 3, and then 5 just stays the same. There's a constant acceleration in the vertical that's changing linearly in the horizontal. And when I plug that in, I have my final acceleration vector. Keep it just as it is. It needs to be a vector. It's going to be 6, 5. So not too bad, not too awful. Just things that we're not used to. I didn't just want to totally breeze over and be like, no big deal, let's rush on. So then remember that Endeavor card. Get it down if you haven't yet already. Endeavor number 32. We did some other basics on Friday. And guys, please, 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 the book has so much information in this. Like, this is one of the longest sections, if I remember right, as far as just like with content. They're doing a lot with planar motion, displacement, distance traveled, velocity, acceleration, speed, and like they really are trying to help you review if you need it. Head minus tail is talking about like the final point minus the initial point. So good vector review if you need it. But before we get into homework questions, and remember I didn't want to require everyone to go through the homework questions with me either, and just a few of you might have kind of lost a couple concepts in how quickly we tried to cover this on Friday and how distracted we were. I'm going to go ahead and, there we go, there's that homework that's due tomorrow, 8 a.m. Right now it's Monday night, in case you're curious as to why I'm saying tomorrow. Here's that extra question that is attached in your Google Classroom. So I want you guys, if you have not done it yet, pause this video, and I'm going to go ahead and stop it for you as well, and go try this. This is the homework due on Wednesday morning. Man, it's going to be hard to keep track of days now. But due on Wednesday morning, our 0 period. Well, maybe make some coffee at home, and if you have something sweet, enjoy it just in lieu of 0 period. But I want you guys to try this example, and then remember, it is due Wednesday morning, attempted and graded. It's due Wednesday morning, attempted and graded. So go ahead and attempt it now, and then when you're done, come on back to the video, and you'll be able to grade it with me. All right, welcome back. So here we go. As we are, example number 9, I'm going to go ahead and zoom in and see how you guys did. What was given to us was an x prime of t and a y prime of t, a horizontal velocity, a vertical velocity. They also gave us a clue. I see a clue in that at t equals 2, remember that's a time, and then I have an xy position of 6, -3. So it's going to seem weird. I have 3 variables. Letter A isn't too bad because it just talks about the acceleration vector and the speed of the object at time t equals 2. Okay, so reminders with acceleration vector, we're just taking a derivative. Hopefully that's good for you guys. And as we take the derivative, acceleration vector, and the speed, ooh, that's going to be exciting. Let's start with the acceleration vector, it's the one that came first. So acceleration vector, as simple as, right? We just need to take the derivative of the derivative. So we're going to go ahead and do d squared x all over dt squared at, where are we going? T equals 2. Everything's in terms of t. And then we're going to need our d squared y all over dt squared. T is equal to 2 as well. The nice thing is, I guess you guys could have plugged in chunks of this by hand. Maybe I should put a quick comment since you guys have just seen this or you're just about to see this. It is a calculator problem. That would have made your lives a lot easier. So I'm going to go ahead and go over to my calculator in just 1 second. But as I get ready to do that, because of course our calculator can numerically derive, aka take a derivative of what you have at a point. We'll see that in just a second. We also are supposed to do speed. And so remember with speed, another way of saying that absolute value of velocity, but in this context of vector, we have to think magnitude. That's going to be the square root of what we already have, which is just going to be our dx dt at 2 squared, and then our dy dt at 2 squared as well. I mean, you could also do if you wanted to, just because the notation is proper and it would probably make your life a little bit simpler and a little bit easier. You could have also just done your x prime of 2 quantity squared plus y prime of 2 quantity squared. That notation probably would have been a bit cleaner. Yeah, definitely a bit cleaner. So then coming over to my calculator, double checking, I think I already have it all plugged in as far as my dx dt and my dy dt. Oh, I didn't have it there. Just kidding. I think I have it in my webcam. There we go. So I have my sine. Oops, that's definitely supposed to be a sine inverse. Second sine. There we go. Double checking real fast. I have my sine inverse of 1 minus 2e to the negative. Now you can't do t, at least not nicely, in this form. I mean, I guess you could have gone to parametric mode if you needed to look at the picture, look at the curve, etc. I just threw it into my y equals because they're both in terms of t and they're not asking me to visualize it, at least not right now. Ooh, they might in a second though. Well, that would have made life more exciting. But either way, I will be able to do the math the way it's written, just in function mode. Then I have my 4t over 1 plus t cubed. If you guys didn't read that carefully, it might have been a little rough. But what I can do right now, in that I need to take the derivative of the first at 2 and the derivative of the second at 2, I can go ahead and just use that little shortcut, or even just use math and then n derive. I can take a derivative with respect to x of that y1, which would be my first function, which in this context was dx, which is perfect. Of t, remember, I just made it in terms of x because that's what I was able to use, but in this one, okay, yeah, it is the t's. When t is equal to 2, so I have my 0.395 as my acceleration, my horizontal acceleration, and then for my vertical acceleration, I could go ahead and just do basically the exact same thing, just instead of y1, let's go get y2. And there we go, our negative 0.741. In context, what does that mean? Well, that's a bit more exciting, but I'm going to get those answers on the page in just 1 second. Let's also while we're here, go ahead and take our square root of. Now remember, we're not taking a derivative because we already have our x prime. So we're going to go ahead and do our, I might just actually get out and do some parentheses. We need our x, our y1 of, which is the same thing as our x prime of 2. Quantity squared plus, then we need to go get our y prime, which is our y2, our y prime, so our y2 of 2 quantity squared as well. There we go. And then we have our speed at the same time. I'm going to get those answers in, and you guys could be thinking of if they were asking you to explain what that meant, as far as the acceleration vector being positive in the horizontal and negative in the vertical. Let's see, 0.396, and then we have negative 0.741 as our acceleration vector. There we go. Go ahead and grade that and see how you did. And then our speed at 2, both of them were at 2, ended up being 1.278. They didn't give us, I don't believe, in this problem any units, which is kind of nice. You don't have to stress about it. But as far as the acceleration goes, we could say that the velocity is increasing. Velocity is increasing in the horizontal direction, but decreasing in the vertical direction. The way of saying that is that velocity is, how can we say that? Moving to the right. Go that direction. That'd be a little rough though. Acceleration, we're kind of just more used to talking about the rate of the rate changing, the rate increasing, the rate decreasing. The struggle is that it's increasing in one direction, it's decreasing in the other. So it'd be kind of like a mixed explanation that you would have to do. And then the speed is more of just a quantity. Now in letter B, when it says the curve has a vertical tangent, tangent line at one point. It wasn't mine, but still. Typo. At what time t is the object at this point? Now, this might be a context or a place where you might have wanted to use parametric mode instead of using function mode, because then you could have actually been plugging in, and bummer is you can't like copy and paste from function to parametric. I just tried it. Because then you could have been plugging in this function, actually looking at it, and maybe you'd be able to see if it makes sense or not. But technically, we don't need to have it in there because, okay, hold on, a vertical tangent line, we're talking about a tangent to the path, a tangent to the curve. That's still just good old-fashioned dy dx. And dy dx in this case, remember, parametric is just y prime of t all over x prime of t. And remember that that's going to be vertical, right, when the denominator is equal to 0. So in this case, denominator is x prime of t, which they gave us right up above, is that sine inverse of 1 minus 2e to the negative t, when that equals 0. And they gave us t is greater than or equal to 0, so we have a little bit of a time constraint, but not a huge one. But the nice thing is we totally have our calculator where we have our function already plugged in if we're in function mode. If we're in parametric mode, we're in a bit of a bummer because parametric mode does not have this nifty 0 feature that function mode does. I'm going to go ahead and deselect y prime for right now. I might bring it back in just 1 second because there is one thing that we haven't considered as to when x prime might be 0 and yet the tangent line might not be vertical. Hence another reason why it might be nice to have that parametric curve picture in parametric mode. But let's go ahead and just find the zeros of sine inverse for right now. We can make our window not go negative, or if you want, just have it go negative just a little bit. You can have it go up if we need it, but we're looking for any zeros. There's one of that curve. Now, it might just be increasing after that point, and if it is, then we're good to go. If you want it to be safer than sorry, you could technically go ahead and just have it go crazy high and be like, are you just going to increase forever? And, well, don't see it decreasing, but if you want to be even more paranoid, you could be like, buddy, what are you doing? I do not see it going down. You could also technically look at x prime of t, that function itself. Remember, x prime does indicate the increasing, decreasing nature of x. I guess in this case, yeah, we could think about increasing, decreasing nature of x, which is like the y when t is the independent variable. So you could look at this derivative and see if it would ever be negative, if the function would ever decrease. This is a tricky function to analyze, though, with 2 over e to the t in common denominators. So let's go ahead and just use our calculator as our guide. As we use our calculator as our guide, let me go ahead and pull up, there you go. I only see 1 0, and so going back to the very beginning of being able to find that or see that 0, the one thing that we need to be very careful of is the vertical, or I should say the tangent line will be vertical whenever the denominator is 0 as long as the numerator is not. As long as the numerator is not. That's the one exception. If I have a 0 over 0, that is not a vertical tangent line. That is a non-existent tangent line. Can I say it that way? The limit may still exist, but the actual quantity does not. I think that's true. So it's not that we have an infinite slope, it's that we have a non-existent slope. Now I know in limits 0 over 0 means keep going, like you keep looking, like there could be a limit. But when we have like an actual quantity equaling 0 over 0, it's undefined. Like it does not exist. Put it in your calculator, there's going to be an error. So the one thing that I am going to do, I actually am going to come back and I am going to graph y prime at the same time and make sure that y prime and x prime are not 0 at the same time. They're not. So I can go ahead and go find the 0 of x prime, making sure I have the right one. I think I could do like a 0.5. You can type in and jump backwards, which is nice. And then you can go at, let's use that 0.5. And I totally did not do my bounds well enough. Let me go ahead and go back to get my 0. 0.5. Oh, I did get my left bound. There we go. And right bound on the other side of the 0. And I have 0.693. There we go. You can pause this video if you guys need to follow what I did. But 0.693 is going to be my time when and y prime does not equal 0, which occurs at t is equal to. You guys enjoying not having to like dodge trying to see this? That's like the very bottom of the smartboard screen. There we go. Making sure I'm in radian mode. Pre-cal kids do on my calculator, but it's looking good. We do have 2 more parts to this, and we're almost done. But m of t, ooh, m, that sounds like slope. Hey, denote the slope of the line tangent to the curve at the point x of t, y of t. Ooh. The slope of the line tangent to the curve. Okay, so m is equal to, we were just talking about the slope of the line tangent to the curve at the point. So it would be such that x of t, y of t. Remember, this is also dy dx is also equal to y prime of t over x prime of t. Well, wait a minute. Hold on. So then, what are they actually asking me to do? Write an expression for m of t in terms of t and use it to evaluate the limit as t goes to infinity. Tangent to the curve. Tangent to the curve is just dy dx, y prime over x prime. Y prime over x prime they gave us up above. Now, ooh, do I still have my calculator? Yeah, I do. That would be 4t all over 1 plus t cubed all over, how are we going to take a limit of sine inverse? Well, I know for one thing, I better help my brain out and move that e to the negative t down into the denominator. So our goal is to take the limit as t goes to infinity of m of t, which we now have an expression for. Okay, so now as we take the limit, sorry, I was double checking the answer up above, making sure I had it right. It'd be a bummer if there's no one here to check me and I got it wrong. Okay, the limit as t goes to infinity of m of t. You can look right up above. Let's check out this guy. What do we have going on? Maybe the yellow marker just so we can kind of like be looking at it together. I see t going to infinity. I see this guy, the bottom winning, which means this expression would be going to 0. As bottom expression, as t goes to infinity, this is going to 0, this specific piece, and yet I still have sine inverse of 1. A sine inverse, for some of us, it's been a little while. Remember, sine inverse is going backwards from sine, asking when sine is equal to, or when the sine curve hits 1. So when does sine equal 1? Sorry, getting probably a little bit rough for some of you to see. That's going to be at pi over 2. But long story short, it's a constant. And guys, what's 0 over any constant? This would specifically be now pi over 2 is only one example. Because technically sine inverse of 1, no sine inverse, it's going to be a restricted domain, so it is just going to be pi over 2. So I can say this is equal to 0 over pi over 2. But remember, just in case you're a little bit iffy on your unit circle, the point is that it's a constant. You don't even have to put what constant. You can just say the limit is 0, which means, hold on, the limit of the tangent line is 0. Doesn't that mean that my curve is flattening? That my curve is flattening. Ooh, flatten the curve. Practical application. Have you guys thought about how the whole coronavirus and all the terminology that you're hearing on the news about flattening the curve, isn't that like a logistic growth idea? That something can grow exponentially, and the sooner we flatten the curve, the sooner we get it to stop with the uphill slopes, like the slopes increasing or the rates increasing, then we can slow this down and fewer people can get infected, etc. There is also, I guess, the scary part that most exponential growths don't start slowing down until you hit half the population. But there again, I mean, that's the ideal world. Math is kind of like apart from all these extra measures that are being put into place. But just very interesting as far as flattening the curve. You guys have some context to think about as far as what they're actually trying to do. The limit is 0, and we're done. Done. P.S. Keep following those repetitive measures, please. Be careful, be safe. Letter D says, to the best of your ability, and then trust God for the rest, right? Letter D says, the graph of the curve has a horizontal asymptote. Ooh, a horizontal asymptote. Wait a minute. Horizontal asymptote. That's just my brain. What am I doing? I'm connecting the wording horizontal asymptote with what an HA actually is, which an HA, remember, I forgot the yellow doesn't write so good. there's an HA at y equals L if the limit as x approaches infinity of y is equal to L. Now hold on, in context, wait. In context, we're not talking about a function in terms of x and an x approaching infinity, so that doesn't necessarily work quite as well. But can't we talk about another way of describing that? If the limit as t goes to infinity of dy dx is equal to, if the curve is flattening, it is getting closer and closer to the horizontal asymptote. So now we just discovered basically there's another definition of a horizontal asymptote that we could have used back when we discovered what limits are, because it's all about the slope of the tangent lines. But back when we were talking about horizontal asymptotes, it was actually before we had done derivatives, so we didn't really use that whole flattening of the slopes, flattening of the tangent lines, but that's another definition. So whenever they say flatten the curve, be like, oh, hey, the slopes of the tangent lines are going to 0. Or hoping to. Right, but to not evaluate an expression involving an improper integral that represents this value. Ooh, what the actual value is. Improper integral, horizontal asymptote. I'll give you guys a second to think about this one, because an improper integral, I need to have some sort of either asymptote itself, like vertical asymptote, which I don't really even think any of our functions do. Sine inverse does have a restricted domain in that I can only be taking values between 1 and -1, but there's no vertical asymptotes in between. T could be -1. Oh, T could be -1. I also have, at time t equals 2, the object, I have an initial position. Initial position. I wonder if they want me going back to position for some reason. Let's ponder just for a second. What did you guys come up with as you were doing this last night? Or this morning, I suppose. Could be checking it before 8 a.m. They need us to get an actual y value. In order for us to get an actual y value, don't we have to go back? Now, in order to go back, we could go back from y prime, right? The definite integral of y prime of t dt should take us back to y. But be careful, we have to actually land on the horizontal asymptote. Wait a minute, hold on. But by definition, a horizontal asymptote, can you actually land on it? If I wanted something like integration is net change, a value at a time b, a final time, I would put that final time up here in the top bound, using the bottom bound as some sort of initial, right? I would start at some sort of initial, something I do know. I would add the change, and I would try to get to where I'm going. But this time, where I'm going is infinity. I'm trying to figure out what or where y of t is headed. So the struggle is, I need to actually have my upper bound be infinity. Now going back and looking at my initial condition up here, that's going to tell me when to start. I have the y value being -3 when t is equal to 2. Now I can't just stop here and be like, I wrote my expression. I need to actually show them I know what's going on with the -3 plus. I'm starting at t equals 2. I need my bottom bound to be 2. They said improper integral, so I am totally allowed to leave that infinity in that bound. But I better go ahead and take that y prime and throw that into the integrand position. So I have that for t all over 1 plus t cubed dt. And that should find for me, check it, what is the limit as t goes to infinity of y? C. And that's exactly what they were asking for up above. All right, kiddos, at this point, go ahead and go back in the video anywhere you need in order to grade, and then remember, go ahead and submit this problem, which I need to remind myself, go tell you before you even see it or as you see it, you are allowed to use your calculator. But go ahead and grade and submit by Wednesday morning, 8 a.m. All right, love you guys, miss you guys, and I will talk to you soon because polar area, ooh, it's a party. Make sure you hopefully have your calculators at home. You were supposed to bring them home. And where we're going next is polar mode. P.S. Look over your unit circle just a little bit because we're going to make tables with thetas. Bye, guys.